Hi everyone! Today let's talk about session 13.3, double integrals in polar coordinates. So last time we talked about double integrals in the Cartesian coordinates, xy, right? If we have like the rectangle regions in the xy plane, then the boundary for x and y are constants. But if the region R is not a rectangle, then we have one variable that's outside, it's between two numbers, and then the other variable is a function of that variable, okay? So today we're gonna look at the double integral in polar coordinates. So we call the polar coordinates r, theta, and their relationships with the Cartesian coordinates x and y. So let me draw a picture. So for points here, theta is the angle it makes with the positive x-axis, right? And then r is the distance from the origin to the point. Then this guy is the x, okay? X coordinate, and this is the y. And what's the relationship between them? We have x equals r cosine theta and y equals r sine theta. Okay, so this can help us so if we have xy, this help us to change in terms of r and theta. Okay, so next we have x squared plus y squared equals r squared, so we can solve for r. R is the square root of x squared plus y squared. Okay, and we know tangent theta is y over x. So what is theta? Well, it really depends on the point. If the point is in the first quadrant, then theta is just arctangent of y over x. But if the point is in the second or third quadrant, then we have arctangent of y over x plus pi, because the arctangent function only cover minus pi over 2 to pi over 2, okay? And some notation of the book, they want to express the theta is positive. That's why if it's in the fourth quadrant, they use arctangent of y over x to plus 2 pi. Okay, but if you use just arctangent, that's also fine. But just if it's in the fourth quadrant, the angle will be negative. Then these together can help us to given r and theta, then we can get x and y. So far so good? Okay, let's continue. Let R be a region in the xy plane. We call that the area of R can be computed using a double integral. So dA is often called the area differential, and in the Cartesian coordinate, dA equals dy dx or dx dy. Intuitively, dA is the area of a small rectangle with base dx and height dy. Okay, so let me draw a picture again. So let's say this is the region R, right? And then we have some surface on top of it, right? And then area differential, this is the dA, okay? And we have, this is x-axis, this is y-axis, then this guy is dx, this guy is dy, okay? Alright, so how about the area differential in the polar coordinate? So a small increment dr in r and d theta in theta will give a rise to an area differential dA as follows. So if we break up the xy plane into a planar grid, the small slightly curve is not quite look like a rectangle, but it's a slightly curved rectangle. Okay, then what are the sides? Okay, so this guy is the change in r, so this is dr, right? But here you cannot just measure the angle d theta, because think about this length and this length. Okay, think about these. The difference of the angle is also d theta, but you can see the length, the difference. So here I want to remind you the length of a sector equals, so a sector here, if this is r, this is theta, and then this length is gonna be theta times r. Okay, so this guy, the change of the angle is d theta, and here the r is the radius is r, so that's why the length of this sector is r times d theta. Then we get this rectangle, so the area of this rectangle is dr times r d theta. Okay, and we usually put the dr and d theta at the end, so we move the r in front. Okay, so that's why our area differential in the polar coordinates equals r dr d theta. So far so good, everybody. Let's look at the following example. Set up and compute a double integral in polar coordinates that gives the area of the disk x squared plus y squared less than or equal to 25 in the xy plane. Of course, we know the answer would be, so this is a circle with radius 5, right? So pi r squared, and then r is 5, so the answer would be 25 pi. We know it's from geometry. Okay, so now let's set up the polar coordinates. Okay, double integral in the polar coordinates. So here what do we do here? Okay, so we have integral 1, and dA is r dr d theta. So let's look at our r. Our r goes from 0 to 5, right? So r values goes from 0 to 5. How about our theta? Well, our theta goes from 0 to 2 pi. So far so good. This is the whole disk. Okay, then let's see. This is 0 to 2 pi. Integral of r is r squared over 2. Evaluate from 0 to 5 d theta. So we plug in 5, 25 over 2, and then d theta, right? So integral of a constant, we just get 25 over 2 theta. Evaluate from 0 to 2 pi. We plug in theta equals to 2 pi. We have 25 over 2 times 2 pi, and minus 0, right? Ooh, the 2 cancel, so we get 25 pi. You see, it match with our answer. So far so good. So a common mistake is students might forget about this r. Okay, so dA is not just dr d theta, it's r times dr d theta. Okay, all right, let's continue. Next, expression general double integral in polar coordinates. Example, find the volume of the solid that lies beneath the paraboloid and above the xy plane. So above the xy plane, okay, what does it look like? So first, you want to find the intersection with this guy in the xy plane. Xy plane means z is 0. When z is 0, we have 4 minus x squared minus y squared is 0. It's the same as x squared plus y squared equal to 4. So, which means on the xy plane, our radius is 2. Then we have a circle like this. Okay, so this is the region R. Okay, the region R on the xy plane. And paraboloid, what's the highest z can we get? This is, you can see it's open down, right? The coefficients of x squared and y squared are negative, and when x and y are both 0, we have z equals to 4. So the parabola looks like this. So far so good, everybody? Okay, and now, well, let's look at the region R. So here, this is the region R, right? And we want to express the double integral in polar coordinates, right? So polar coordinates, the function is 4 minus x squared. So first of all, I want to show you what happens if we want to set up the double integral in the Cartesian coordinates. Okay, so in the Cartesian coordinates, here the order doesn't matter. We can do dy dx or dx dy. So let me do dy dx, which means I cut it vertically. Okay, so that's dx. Well, this corresponds to y equals square root of 4 minus x squared, negative of that. The up, we have y equals the positive square root of 4 minus x squared. So y is a function of x, okay? And then the x goes from -2 to 2. So this is what we would do for Cartesian coordinates, okay? Like what we learned before. But now, can you see this is a circle? So circle is easier to compute using polar coordinates. I can show you why. So here in polar coordinates, we're gonna have the function. So we're gonna have the function in terms of r and theta. Well, can you see this guy? Z is like 4 minus parentheses x squared plus y squared, but x squared. So here when you change, keep in mind that x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. So that's why here we get 4 minus r squared. So this is the function, and the area differential equals r dr d theta. Then what is our r? Our r goes from 0 to 2, right? R goes from 0 to 2, and our theta goes from 0 to 2 pi. See? Now I don't need to deal with the crazy square roots. My boundaries, they're just constants. So it's much easier to integrate in this case. So what is that? Let's evaluate this integral. First, we don't have product rule or quotient rule, so distribute it. So we have 4r minus r cubed dr d theta. Integral of 4r is, so with r squared divided by 2 become 2r squared, r to the 4 divided by 4, evaluate from 0 to 2 d theta. And here we plug in 2 squared, 4 times 2, 8, 2 to the 4th, 16 over 4, 4. When we plug in 0, it's just 0, and then d theta. So you can see it's 4. So the integral of 4 with respect to theta is just 4 theta, evaluate from 0 to 2 pi. So we plug in 2 pi, minus we plug in 0. So the answer is 8 pi. See, much easier than calculating these square roots, right? So when do you use polar coordinates? Well, if you see the base region is related to a circle or like a portion of a circle, think about polar coordinates. Okay? So when the base region is like a disk, then you think about polar coordinates. Okay, it might make your integral much easier. Let's continue. Okay, So let R be the region in the xy plane given by the inequalities. So pi less than equal to x squared plus y squared less than equal to 2 pi, and y is greater or equal to 0. Okay, so let's draw it. Here it's like we have two circles. One circle is x squared plus y squared equals pi. Then the radius is square root of pi. Okay. And then we have a bigger circle. Oops. Let me make it more round. And then the bigger circle, x squared plus y squared equals 2 pi. And then this is square root of 2 pi. It's the biggest circle. Let me draw a round circle. Okay, and y is greater or equal to 0. So this is the region. So far, so good, everybody. Okay, so now let's set it up using polar coordinates. You can see the base region is in terms of like circles, between circles. So it's better to use the polar coordinates. And x squared plus y squared is r squared, right? And then dA will be r d theta. And we really need the r because we are able to integrate this integral because we can use u substitution. Let this be u, and then du is 2r r, right? Without this r, we get stuck because there's no way we can integrate this guy. Okay, so, and then now, what is r? Well, r goes from square root of pi over 4 to square root of 2 pi. Sorry, square root of pi, not pi over 4. Why do I say pi over 4? Interesting. Okay, how about our theta? So our theta goes from 0 to, what is this guy? This is pi. So far, so good, everybody? Alright, so this is the theta values. So let's integrate. Well, u substitution, u be r squared. Du will be 2r dr equals 1/2 du, and then the inside integral is like, okay, u of square root of pi, u of square root of 2 pi, and then we have sine u du 1/2. Let's move it in front. Okay, so the integral of sine u is plus or minus cosine. Think about the derivative of cosine is minus sine, so integral of sine is minus cosine. And now u of square root of pi, u is like r squared, right? So square root of pi squared is pi. And then this is 2 pi. Okay, and then we have d theta. We can also move out the 1/2 and the negative as well. Okay, then cosine, cosine 2 pi minus cosine pi d theta. Okay, do you know cosine what it looks like? Here, cosine 2 pi is 1. Cosine pi is minus 1. So that will give us 2, okay? This is 2. So integral of a constant 2, we just have 2 theta. So minus 1/2 2 theta evaluate from 0 to pi. And then this cancel, we plug in pi first, then we plug in 0, 0 is gone. So this is what happened. So far, so good? Yeah, the area is, the double integral is negative because this is a signed volume, okay? Sine, so think about if R is r squared is between, so if r is between square root of pi and square root of 2 pi, then r squared is between pi and 2 pi. What does the sign look like? Sign from pi to 2 pi, the sign is negative, so sine r squared is negative. Okay, so which means on top of our region, so on top of our region, actually the surface is under the xy plane. Okay, the surface is under the xy plane. That's why the volume, because this volume, this solid is under xy plane. So the volume is assigned volume. Okay, the double integral is negative. So far so good, everybody? Okay, so let's continue to look at more examples. Compute the following double integral. So it is giving us Cartesian coordinates. So let's draw the picture and see what it looks like. So in general, it is enough to draw the region in the xy plane. Then we can change, we know how to change to polar coordinates. And then you don't need to really draw the function in the space, okay? Because the function will be the same function, but just replace x by r cosine theta and y by r sine theta. And when you see x squared plus y squared together, you can simply replace it by r squared. So let's draw the region in the xy plane. Okay. So let's see. Our y goes, so this is the y. It goes from and our x goes from y to square root of 1 minus y squared. Okay. So y is from 0 to 2, root 2 over 2. Okay, but let's figure out what is x. So x equals y. What does x equals y look like? This is x equals y. And x equals square root of 1 minus y squared. Well, this is the same as saying x squared equals 1 minus y squared, so x squared plus y squared equals 1. So this is a circle center at the origin with radius 1. And my circle doesn't look really like a circle. Let me draw it better. Is it better? Okay. Now let's see. X is from x equals to y here, and to the circle, so this pieces, okay, this dy, and then y goes from 0 to square root of 2 over 2. So actually this point is square root of 2 over 2, and this is 1. So far so good. So this is actually tells us this is the region R. So from this double integral, we can figure out the region R on the xy plane. So in the xy plane. Okay, so now let's change it to in terms of polar coordinates. We have the function, we place it by r squared, and then the area differential is r dr d theta. Okay, now our r, see, our r goes from this region, r goes from 0 to 1, but the theta goes from 0 to, any guess? Which angle? Pi over 4. Right, everybody? Now you can see they are just constants, right? R and theta just between two numbers. So so that's why when you see circles, make it in terms of polar coordinates can make the integral much easier. And furthermore, here because of the r, we can do u substitution, because we can let u be the denominator, and then right, du will be 2r dr. R dr is 1/2 du. Okay, so 0 to pi over 4, and then here u of 0, u of 1 over u. R dr is 1/2 du, but 1/2 we can put in front, and d theta. Sometimes you can put it in the front. Okay, and then here integral of 1 over u is ln of absolute value of u. Now we can change to the u values. U of 0, 1 plus 0 squared is 1. U of 1, 1 plus 1 squared is 2. So far so good, everybody. So this is 1/2 integral from 0 to pi over 4 ln of 2 minus ln of 1 d theta. Alright, so we have 1/2 ln of 2 minus ln of 1 times theta, and my theta goes from 0 to pi over 4. So we plug in pi over 4, that will give us pi over 8 times ln of 2 minus, ln of 1 is just 0, right? So it's just pi over 8 times ln of 2. That is our final answer. So far so good, everybody? Okay. So yeah, this example is a typical example. We're given double integrals in Cartesian coordinates, and we need to draw the picture in the xy plane, find out the region R, and then set up the double integral in polar coordinates to evaluate. Let's continue. Find the volume lines between the surface z equals 3x squared plus 3y squared and z equals 4 minus x squared minus y squared. Okay, so here, what are the surface look like? Well, this guy, this like is a paraboloid, but it opens up and it passes through the origin, right? So it looks like this. And the other one, this is also a paraboloid, but it opens down, right? And when it crosses the xy plane, we get 4 minus x squared minus y squared equal to 0. Okay, so when it crosses cross xy plane, we get 4 minus x squared minus y squared equals 0, and x squared plus y squared equals 4. That is the circle with radius 2, and it passed through 0, 0, 4. Okay, so it looks like this. Okay, then now you can see those two paraboloids, they intersect in a circle. So, and then we can project this circle down on the xy plane. This is the region R. So this example, we have to be very careful because the region R is not x squared plus y squared equals 4. It's whenever they intersect, okay, because we're looking for the volume that lies between the surface. We need to find where they intersect. Okay, how do we find where they intersect? Well, solve the system of equations. Well, z are equal, so just set them equal. So move all the x squared, y squared on the left. We get 4x squared. 4y squared equals 4. X squared plus y squared equals 1. Oh, so this intersection, when we project down to the xy plane, it is actually a unit circle. Okay, so our region R is a unit circle. Okay, this is the region R. Is a unit circle. Okay, now we can set it up. So we use polar coordinates, right? And then we have the upper surface. Which one is the upper surface? This guy is the upper surface, right? Minus the lower surface, which is 3x squared plus 3y squared. By the way, you gotta make sure they are in terms of z equals function of x and y. If it's not, then you probably need to solve for z. Okay, everybody? Because the height is a z. So this is the same as 4 minus 4x squared minus 4y squared, right? And now let's use polar coordinates. Change x squared plus y squared to r squared. So this is the same as minus 4r squared. Is that okay? Okay, let me do it slowly. I can factor out 4, and then I have x squared plus y squared. This is the same as r squared if we want to use polar coordinates. But then dA is r, dr d theta. So don't forget the r is very, very important, and many students make this mistake. Okay, now look at this. The inside is r, so my r goes from, look at my circle. My r goes from 0 to 1. See, it's 1, it's not 2. Be careful. And the theta, it goes one circle, the disk, so 0 to 2 pi. Okay, so I would say the typical error here would be students forget about this r, and students didn't figure out the intersection circle. The radius is only 1, it's not 2. Alright, let's continue and evaluate the integral. So we don't have product rule or quotient rule, so we should distribute it. Then we have 4r minus 4r cubed dr d theta. So integral of 4r is, okay, r squared over 2 r squared. R to the 4 over 4, 4 cancel, r to the 4th. From 0 to 1, d theta. So we plug in 1, we get 2 minus 1, and when we plug in 0, we just get 0, and then d theta. So this is just 1. Integral of 1 with respect to theta is just theta, 0 to 2 pi. So the answer is 2 pi minus 0, which is 2 pi. So far, so good, everybody. So the region between the two surfaces, the volume of that region between the two surfaces equals 2 pi. A very nice number. So far, so good, everybody. Yeah, so this example, just be careful. We need to find the intersection. Okay, so let me use a different color to emphasize. We need to find the intersection, okay, of the surfaces, and then project onto the xy plane to get the region R. Okay, and then depending on the region, if it's like a circle, then we would use polar coordinates. All right, let's continue. Okay, so review of special circles. So let's recall that the polar equation of circles passing through the origin with diameter on one of the coordinate axes. Okay, so through the origin. Okay, so circle passing through the origin with the diameter on one of the, so this guy, let's say if the radius is a, well then this point is a0, right? And we know the circle equation, we get x minus a squared plus y squared equals a squared. So how do we change it to polar coordinates? Well, first of all, let's distribute it. So when we distribute it, x squared minus 2ax plus x squared plus y squared equals a squared, right? We multiply out. Oh, you can see a squared cancel. And then we have x squared, y squared. When we see both guys together, we always put them together. Okay, x squared plus y squared change to polar coordinate. This is r squared. And x is r cosine theta. Well, this is the same as saying r squared equals 2a r cosine theta. So here we can get r equals 2a cosine theta. And this solution already include the solution when r equal to 0, because when theta equals pi over 2, r is 0. So it already includes solution when r equal to 0. So polar equation, r equals 2a cosine theta. How about on the other side? Similarly, we have the center as 0a, we expand it, then we have minus 2ay plus a squared cancel, x squared plus y squared is r squared, and we can get 2ay, y is r sine theta, and then r is 2a sine theta. So when you see when theta is 0, we already include the solution when r is 0. So that's why here we get r equals 2a sine theta. See, very simple polar equation. Now with this in mind, let's look at the following example. Find the volume that lies beneath the cone and above the disk. Okay, this disk, which one? So see, the A is on the x-axis, so which is this guy, right? So, and A is 1. So we have r equals 2 cosine theta. Okay, this is our circle. Alright, let me try to draw it and show you what happened. What's the picture look like? So in space, this is in the space, right? And this is a circle like here. This is 1. Okay, and we have a cone on top of it. Okay, so and if you want to draw it here, so this cone, if we project this cone up there, you will see this region. So this is a solid. Okay, we want to find the solid that lies beneath the cone and above the disk. Okay, so here on the xy plane we have this one, and let's try to use the polar coordinates. Okay, so you can see this is symmetry about the x-axis, right? Instead of so this is the region R, and we have beneath the cone is square root of x squared plus y squared dA, right? And when we use polar coordinates, you can see because it's symmetry about the x-axis, so it's enough to just look at the top region and then multiply by 2. Is that okay? We look at the top region and we multiply our answer by 2. And then what is square root of x squared plus y squared? This is just r. and dA is RD theta. Now let's look at the R. What is R? Well, R goes from R goes from 0 to this circle R equals 2 cosine theta, and my theta goes from 0 to, what is this angle? Pi over 2. Okay, we can also do minus pi over 2 to pi over 2, but it's easier to calculate from 0 to pi over 2 and then multiply our answer by 2. Because in the first quadrant, a lot of like trig functions are positive, so we don't need to worry about the sign change. And yeah, a lot of sign change can like create mistakes. So be careful with that. So let's continue. Here we have R squared, right? And then integral of R squared is R cubed over 3. Evaluate from 0 to 2 cosine theta d theta. Yes. So this is a special example that not both of R and theta are constants. So R is the function of theta. So let's see. So we plug in 2 cosine theta first. So we have 8. 2 cubed is 8. Cosine theta cube over 3. Then when we plug in 0, it's gone, right? So we want to calculate this integral. So I really hope that you're familiar with all the trig identities and double integrals. And also, Cal 2, session 7.2, we talk about trig integrals. So here, if you have an odd power of cosine, you can split. So first of all, let's move all the constants outside. We can split a cosine at the end and then change the remaining even power. So change it in terms of sign. So cosine squared is 1 minus sine squared. Okay. Now we can do u substitution. Let u be sine theta. Du is cosine theta d theta. So this is 16 over 3. Integral u of 0, u of pi over 2. 1 minus u squared du. This 16 over 3. Integral of 1 is u. Integral of u squared is u cubed over 3. Evaluate from u of 0. So sine of 0 is 1. U of pi over 2, sine pi over 2 is 1. So we plug in 1. We get 1 minus 1 over 3. When we plug in 0, it's all 0. 1 minus 1 over 3 is 2/3. So this, oops. This is 16/3 times 2/3 is 32 over 9. Okay, so this is the final answer. So far, so good, everybody. Okay, yeah, so I hope that you can go to my Cal 2 course and look at the session 7.2. It's about trig integrals. So when you have products of sine and cosine, if one of them is odd, you're going to split the extra factor at the end, and then remaining for the even factor, change it in terms of the other trig functions. Then you can use u substitution. Or you might have products of powers of tangent and secant. And we also have like 3 cases. If the power of tangent is odd, you want to split secant tangent at the end and change the remaining even powers in terms of secant, and if you have secant is even, then you split secant square at the end, change the remaining in terms of tangent, and you also do use substitution. Okay, so if you have powers of sine, cosine, and if both of them are even, you can use the double angle formula to double the angle, reduce the power. Okay, so please watch my Cal 2 notes in session 7.2 for more details. Okay, so that's it for today. If you have questions, don't forget to ask me either in class or through office hours, or send me an email. Have a nice day. Bye.